Good morning, afternoon or evening, whichever it may be. In the last episode we learned about generating a system clock. In this episode we're going to do some essential basics on bits, bytes, hex and buses. Roll the titles.
Is that it?
Now at the end of the last episode I said we'd cover all that I've just mentioned and also 6502's reset sequence. And as before, I've now realised this is going to make for too long a video. So we'll be doing the 6502 startup sequence next time. This episode is going to cover what may be for some basic stuff. Binary, bits and bytes. Converting to and from decimal and binary. Incrementing binary numbers. Hexadecimal, microprocessor buses and their link to binary. So obviously, if you feel you won't benefit from anything in this video, then please come back next time, but on your way out, hit that like button, then the algorithm gods don't get too angry about a short average watch time. I apologise if this is too basic for you, but I want to make sure, going forward, that everyone has a good grounding in the basics before moving to more advanced stuff. If you're still here, then buckle up. We're going in. Most of us may remember some maths lessons in school, or should that be math, as they say over the pond. The USA is my top country for viewers, so thank you to all my North American viewers managing to understand my particular Northern England accent. Very much appreciated. I'm digressing. Maths lessons. Yes, right. Back in school, you usually got taught about different number systems, or usually referred to as number bases, usually binary and octal and perhaps others. In everyday life, we use base 10 or decimal. So we have 10 numerals from 0 to 9 representing the digits that we use in decimal. Unlike Roman numerals who use an X to represent 10, there is no individual numeral or symbol for 10 in decimal. 10 is written using existing numerals. We use a 1 followed by a 0. I'm going to hazard a guess that you probably knew that. So what about binary? Binary is base 2 and has just two numerals, 0 and 1. We have no individual numeral to represent anything higher than 1. So in binary there is no symbol for 2. 2 in binary will be written as 1, 0. The number 10 would be this in binary. 1 0 1 0. The question is, why? Well, going back to when you were around 5 or 6, you were taught all about units, tens, hundreds and thousands, and it went a little bit like this. You had columns for each position of a number, starting with the units, and tens, hundreds, thousands, etc. If we count up starting from 0, we get to 9. No shock there. We add another 1 and we have no symbol for 10. So we write a 1 in the tens column and a 0 in the units column to say we have 110 and 0 units. And you can see that if we carried on adding 1, then eventually we would have 2 tens and no units, etc, etc. Nothing new to see here. I know that's what you're saying. Nothing new to see here at all. Binary, or any other number base, is just the same, except that the column headings go up in multiples of whatever the base is. So let's put our column headings in for binary. Starting with the units, then 2, 4, 8. Each binary digit in these columns is referred to as a bit, a contraction and merging of the two words, binary and digit. Now generally, in binary, we don't write down the word units. We just write a 1 in that column. In other words, how many 1s do we have in this column? And of course, as it's binary, it will be either 0 or 1, no other options. We'll do the counting up in ones thing again. So we start at 0, add 1. We now add another 1. But of course, there are no other digits after the 1 in binary. So we have to put a 1 in the next column and 0 in the first. You can see that we now have 1, 2 and no units. So we have the number 2 but in binary. Add another 1, we now have 1, 2 and 1, 1. In total, we have 3 in binary. Sorry, 3 in decimal. Well, it's still 3 in binary, it's 3 in decimal, but the binary representation of 3. Exactly what we would expect after incrementing 3 times. Let's clear that and put our numbers, let's clear that and put our number 10 in binary into these columns. We can see that we have 1, 8, no 4s, 1, 2, and no units. In total, adding the columns together, we get decimal 10. Bingo. As you're following this series of videos creating a 6502 based system, I'm going to guess you'll know that 8 bits makes 1 byte. And putting in our column headings here will give us values up to 128. Let's put 0 in. Now, in just about every other number system, you don't put in leading zeros, but quite often, especially when showing bytes, you will see leading zeros displayed. Just as I filled in every column here, the maximum value a byte can hold is when all the digits are 1s. Just like the maximum value for, say, a 4-digit decimal number would be 9,999. What is this value? Well, you're probably ahead of me and saying 255. Just pause the video and add up the columns if you're not too sure. For practice, if you want to, pause the video and convert 11010011 to decimal, and I'll give the answer next. Adding up the column headers gives 128 plus 64 plus 16 plus 2 plus 1 equals 211. What if we want to go the other way? Convert a decimal to binary, let's say the number 25. How would you go about that? Well, there is more than one way, but the way I learned from a book from a long time ago was to go down the column headings, and the first one that is the same or less than the number you have, you put a 1 in that column and subtract whatever that column number was from your decimal value. In this case, the first column going from right to left that is smaller or the same as 25 is the 16 column. So I put a 1 in that column and subtract 16 from 25, leaving 9. I then carry on using the same procedure. Next column is 8. Is that smaller or the same as 9? Yes. So I put a 1 in and subtract 8, leaving 1. Next is column 4. No, that's too big. And 2's too big. But 1, obviously, is the same. So we put a 1, then we subtract 1, leaving 0. We've finished. So 25 in binary is 11001. If you want, you try 59. Pause the video if you want to have a go. First, that fits is 32, leaving 27. 16 fits, leaving 11. 8 fits, leaving 3. 4 doesn't, so 0 there. 2 does, leaving 1. 1 does. Hopefully you got that. So where's all this fit in with computers and processors? Apart from the fact that you know you've already been told they work in binary. Well, here's our processor. For this example, we're using the 6502, but it could be any processor, from the 8 bits to the more powerful 64-bit systems of today. It has a data bus for sending values to or from memory. Notice it consists of 8 electrical connections, or a byte, 8 bits. These electrical connections can be a high voltage, usually 5 volts on the older processors, 3.3 volts on the newer, or a low voltage, 0 volts. Those are the only 2 values there can be, so they are binary. You'll notice they are labelled as D0 to D7, corresponding to these positions in our byte. A high voltage represents a 1 and a low a 0. So the processor can send out any number between 0 and 255, which is a total of 256 different combinations of 1s and 0s. We also have a thing called the address bus, and on the 6502 it consists of 16 connections labelled here as A0 to A15. The processor can put a binary value on this address bus that is up to 16 bits in length. The maximum column is now 32,768. If we were to add all these together, you will get a value of 65,535. This is the maximum value that this address bus can handle. The address bus is used to tell the rest of the computer, quite often the memory, what location it wants to either store data to or get data from. And this can be from address location 0 to address location 65,535, which is 65,536 different memory locations, or, as you may have commonly heard, 64K. If you want the byte to address, say, 4045, then send out the binary pattern for 4045 on the address bus. Want the byte at 65,517? Send out that binary value on the address bus, and so on. Hexadecimal is the number base 16, so instead of having just 2 digits for binary or 10 digits for decimal before we have to move up a column, we have 16. For 0 to 9, we use our familiar digits 0 to 9. Makes a lot of sense. But what about symbols for 10 up to 15? We need new symbols. Well, back in the mists of time, they weren't about to invent new symbols and have to try and get them onto some sort of keyboard. This wasn't going to happen. No way, Jose. So taking a sort of leaf from the Romans, they used letters, starting at A for 10, B for 11, etc., up to F for 15. At that point, there are no more symbols, so to represent 16, we would have to roll over into another column as we do with any number base. Let's do our incrementing exercise again. 0 to 9, easy enough. And now when we add another, we get 10. And we do have a symbol for that, so we can stay in the units column. Then add another for 11, and we have B, etc., up to F for 15. We then increment again, which, as we have got 16, must be the number of 16s we have. In this case, 1, and we have no units. So 16 decimal is 10 in hex. Add another and we get 11, which is 17 decimal, etc., etc., until we get to 1F or 31. We have to add another 16, giving 20 or 32 decimal. In this way, we can count all the way up to FF. Can you work out what that would be in decimal? Pause the video if you want to have a go. F is decimal 15. So we have 15 16s, which is 240 decimal. We have F units, which is 15. So 240 plus 15 is 255 decimal. Wow, that's the same as the max value of a byte. Who'd have thunk it? And that's no coincidence. Hex was created so that it was easier to convert numbers into binary and vice versa. Well, at least that's one of the reasons. If you look at a byte, you can imagine it has two smaller 4-bit groups. In the early days, some of the first processors were only 4-bit processors, not 8-bit. A collection of 4 bits or half a byte is known as a nibble. Those early computing pioneers had a great sense of humour. 4 bits gives you values from 0 to 15, which is exactly what hex does. Each digit of a hex number is effectively 4 bits, so FF fits neatly into a single byte, like this. What about, say, the hex number CE? Well, the C is the first 4 bits of the byte and has the decimal value 12. So we can do our trick of converting 12 to binary, giving 1100. Note that for each nibble, we just have the columns for the first 4 bits of a binary number. The second half of the byte, or E, is 14 decimal and will give 1110. Most seasoned programmers, especially low-level hardware types, will know the binary patterns for each hex character in their heads. But any of you don't, converting a binary number no bigger than 15 is not too bad, is it? So, quick test. If 65,535 is the maximum value of the address bus in decimal, what is this in hex? Pause now if you want to have a go. Well, the max value of the address bus is 65,535 is when the 16-bit binary number is all ones. Split this into the 4 nibbles we have, and each is 1, 1, 1, 1. We know that this is 15, or F in hex. So 65,535 must be F, 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 F in hex. In old computing manuals, you would often see memory addresses labelled in hex or decimal, or sometimes both. Obviously, nowadays we have converters of hex, binary, etc. Why should you learn the ins and outs? Well, it really helps that you understand how the bit patterns are formed from these numbers, especially when you're closer to the hardware, as we will be in our 6502 system. That's it for now. I really hope you've got a good grounding in number systems and binary now. This will help with the 6502 project as we go forward. As usual, we all appreciate a thumbs up. YouTube channels more than most, so you know what to do if you want to be so generous. You'll find affiliate links for all the hardware shown so far in the video description. Appreciate if you click one of them, even if you don't purchase the thing you click on, especially if you're from the States, as I'm trying to get on their affiliate program. So I have to have so many qualified sales in a given time. So if you are from the States, really appreciate if you click one of the affiliate links. You don't have to buy the affiliate linked item. You can just click the link, get to Amazon and order anything you want. You know, whatever it might be. Soap powder, a new computer, a piece of Lego, whatever you want. Appreciate the click. Thank you to my patrons. And ways to say thank you or support are in the video description for anybody else that's interested. And finally, thank you all for watching. Cheerio.